Hello, everyone, and welcome to another wonderful day of chemistry. So, last time we left off looking at the temperature dependence of phase transitions. However, one of the more important ones that we're really going to look at today is how pressure can control phase transitions. And it's worth noting, this is one of the topics of a lot of interest for both engineers because they're very interested in pressure dependency, especially chemical engineers. And if you're interested in geology, today's your day. So we're going to really look at how we can use pressure to modify and control phase changes. So we can use the same basic principles we did last time. The idea that what we're really using is the idea of chemical potential, because it's when the chemical potential of the two phases are identical that we're going to see that phase change. So we have to look at how the chemical potential of each component changes with pressure. Now, we're going to be looking at this isothermally because, again, we can use the state function to split up our variances. And if we go back to our fundamental equation for Gibbs, we'll see that the variance here is going to be molar volume. So notice last time it was a negative variance, this time it's a positive. And molar volume will always be a positive property. So as I increase the pressure, the chemical potential will always increase, meaning the system will be less stable. So we can look at this by taking our transitions from last time. So last time we looked at, as I increase the temperature for a solid, we have the energy go down, and then eventually the liquid undercuts it. But as I add pressure, what happens is everybody's line is going to go up. So the solid will become less stable and the liquid will become less stable. So both those lines will shift vertically. But the real issue here is who's going to shift more. So the idea here is that the lower the molar volume, so the more dense the substance, you'll have a lower shift. And this is going to be true for most substances that the solid is going to be less dense than the liquid. So the liquid tends to shift more and it will be more destabilized by this increasing pressure than the more dense solid. Now, when I do this, what that means is that the fusion temperature or freezing point will essentially shift to the right because, again, we're going to end up favoring stabilizing the more dense substance. So the solid becomes more stable for a longer region of temperature. However, we can also flip this. So for water and a couple of other novel substances like gallium, it turns out that the solid is more dense than the liquid. So the solid becomes extra destabilized and the liquid only slightly. Now that means that the temperature is going to drop, again favoring the less dense or the more dense substance. So again, favoring the liquid. And we're going to generally see this as the case, that whenever we're looking at these phase transitions, we're always going to stabilize the more dense substance, and the fusion temperature will go ahead and move to compensate. Now we can examine this a little bit more in detail by, we're going to examine this a little bit more for a vaporization system. So again, looking at the chemical potential of a gas when it's equal to the liquid, that's when we're going to see vaporization occur. Now we can model how that for a gas, we're going to assume an ideal gas. So at this point, the molar volume can be substituted using the ideal gas law as RT over dP. However, for a liquid, that molar volume won't really change, and so this will be relatively invariant to pressure. So we can then go ahead and look at how these changes occur. Now, one of the things to watch out for is when I'm setting equivalency in between a gas and a solid, I have to really watch out for what pressures I'm using. Because the pressure the gas really cares about is going to be the vapor pressure. And it's going to be, because it's ideal, invariant to the total pressure. However, the condensed phases, so solids and liquids, really care about the total pressure. So I'm going to designate the total pressure as uppercase P, and the partial pressure or vapor pressure is the lowercase p. Now what we can have to do is go ahead and integrate over both sides to see how they're going to change as I increase the pressure. Now we're just going to really be increasing the kind of the pressure of the system. So as I go from my initial vapor pressure to my new pressure, uh, to the ambient vapor pressure, we're going to go ahead and integrate on this left side. The RT can come off, and we're integrating P over dP. Now on the right side, we're going to have to start from our initial pressure, which may be just the vapor pressure, maybe something else. And what we're really going to care about is the difference in the application of pressure. So how much the total pressure changed. And this actually gets really kind of fun because we can see how much if I increase a total pressure, how much that will make the system more volatile. And so, since we got dP over P here, we're going to be looking at the natural log of the initial vapor pressure versus the pressure versus how much applied pressure I put on the system. Now, because the molar volume is going to be relatively invariant, we just get the molar volume. We'll move the RT over to this side. And what we can find is the natural log of this vapor pressure ratio is going to be equal to the molar volume, again, of the liquid over RT times how much pressure I applied to the system. Now, when I do this, I can rearrange to solve for my new pressure as a function of my initial vapor pressure. And we're going to find the vapor pressure is going to change exponentially with respect to the molar volume times the change in pressure. Now, the important thing here, as we saw a little bit in the last chapter, is the molar volumes of our liquids tend to be relatively small. So despite the fact this is exponential, we're going to see a relatively small change in that vapor pressure unless I get to relatively high applications of pressure, even with this kind of exponential behavior. So that's something to kind of keep in mind. That in general, that applied pressure is going to have a relatively small impact, but we can indeed predict it with a relatively simple equation. Now, let's go ahead and look at a more general phase boundary in between two phases. And we're going to try and apply some conditions to see how it changes with pressure. So again, as always, we can go to our fundamental equation. So our chemical potential is going to have a pressure dependence and a temperature dependence. The temperature dependence is, again, going to be based on the molar entropy, and the pressure dependence is going to be based on molar volume. And it's going to be true for both phases, so I can set them equal to each other. And then look at the relationship in between the change in temperature and the change in pressure. So one of the first things I'm going to want to do is go ahead and move all of the temperature terms to one side and all the pressure to the other. So we're going to move the temperature, which is going to become my independent variable, to the right, and my pressure is going to move to the left. Now, when I do this, we can pull the dP terms out in the dt, and what we have is going to be the change in the molar volume times dP times the change in the molar entropy times dt. So we can rearrange this as what's known as the Clapeyron equation. So this ratio of change in pressure to change in temperature, which is really going to be the slope of my phase change of my phase boundary, is going to be based on this ratio of entropy of transition to the volume of transition. So this is actually a fairly useful equation and relatively robust. Notice we made almost no assumptions, despite except for the small assumption that we're assuming that the molar volume and the uh, molar entropy aren't going to be changing significantly with pressure and temperature. But for small changes, this should work fairly well. The issue is that we tend not to really look at the entropy of transition because this is going to be a lot harder to measure. Instead, what we like to do is substitute out for the enthalpy. But note, if we're looking at a phase boundary, that assumes the system's at equilibrium. That means I can replace the entropy of transition with enthalpy over T, because these two will be equivalent at an equilibrium or at the phase boundary. So the Clapeyron equation is more often expressed as this ratio of change in enthalpy over temperature times change in volume. Now again, here we have to watch out because we have more of an explicit relationship in between the temperature and the change in temperature. So we can look at this for both of our systems. So we can first apply our Clapeyron equation to that solid liquid boundary. Now in the solid liquid boundary, well, that the enthalpy of fusion will be relatively constant, and that change in volume is also going to be relatively constant because we're going to have a relatively low temperature and pressure dependence on the volume. So at this point, we can simply just move the dt term over to the right, treat the enthalpy and volume as constant, pull them out in front of my integral, and then simply integrate the change in temperature versus the change in pressure. Now on the left, this is going to be relatively simple. It's just going to be the difference in between my initial pressure and my new pressure, again, on that boundary, because we're really tracking that line, is going to depend on the natural log of the ratio of temperature. So again, we do have kind of this odd behavior in between the natural log and pressure, meaning we're going to have a little bit of an exponential change. But notice that we're looking at relative differences in temperature. So oftentimes this means that we're going to have, for most respect, we're going to have, for small changes in temperature, relatively large changes in pressure. Again, this is often going to be highly mediated by the enthalpy of the change in enthalpy and the change in molar volume. Now, we can go ahead and try and simplify this temperature expression using a couple of log tricks. So if we go ahead and assume relatively small changes in temperature, we can do a classic mathematical trick where we can just add 1 inside the log, which should not change the log because that's the same as just adding 0 to the system. Now we do this so we can add 0 inside the log, which is going to be, which we can do by essentially adding in the uh, initial vapor pressure initial temperature of transition over the initial temperature transition minus temperature transition over temperature transition. So notice this is just adding 0 inside the log. But what it does is it lets us rearrange. So I can pull this first term out in front, and that's just the 1. And then I can combine these second two terms as t minus t star over t star. Again, should work. Now, what we find here is we can make use of a common idea that we can do a exponential expansion. So natural log of the 1 should more or less just drop out because that'll be 0. And then we can do this kind of power expansion. As long as this difference is relatively small, this first term is going to end up modeling this natural log of t. So what we can do is we can substitute the natural log of the temperature ratio for the difference in temperatures over the temperature difference. So long as this term is relatively small, so we're looking at relatively small relative changes, which since we're working in Kelvin should be pretty easy to accomplish, we can now substitute in this new idea where the change in the temperature of fusion over the initial temperature of fusion can now be substituted in. So what we can now do is find the change in pressure is going to be related to the change in temperature, showing that we really have a straight line in between these two. Again, for small temperature differences. And we have a prefactor that's now based on the initial temperature, enthalpy of fusion, and molar volume, all of which should be relatively easy to find. And so we can now calculate our new pressure on the boundary condition based on that initial pressure and the change in pressure. So again, really showing we kind of have a straight line expression for solid liquid phase boundaries. And if we look at most of our plots, this is indeed what we've seen. Now, is worth noting, you can also apply the same idea not just to solid liquid, but to also solid boundaries. And that's really useful. However, we're often going to be a little bit more interested in the vaporization. So if I look at the vaporization of a liquid, and again, we can apply the same idea to sublimation. We can now apply our ideal gas law, and this turns our Clausius equation to something called the Clausius-Clapeyron. So let's start with our Clausius expression. Now what we can do is to say that most of the change in volume for a vaporization is just going to be the volume of the gas, because the initial volume of the liquid should be very small and relatively negligible. Then, because I'm looking at the volume of gas, I can use the ideal gas law to substitute in the molar volume is just going to be RT over P. All right, now notice we've got two temperatures, so this now just becomes RT squared over P. Now note, we have some pressure terms and we have some temperature terms. So we're going to go ahead and move all the pressure terms to the left, the temperature terms to the right, just like before. Now what we can now do is use our old trick of knowing that 1 over P dP is just going to be the change in natural log of pressure over dt is now going to be based on this nice, relatively familiar form, the change in enthalpy over RT squared. So now we can move that dt back over and we can really look at this phase boundary. So we can integrate both sides to look at uh, the, the change in the vapor pressure with the temperature. Now, on the left-hand side, this is going to be relatively simple. It's just going to be the natural log of the change in pressure. On the right, we're going to assume that enthalpy is going to be relatively temperature invariant. The enthalpy of vaporization is relatively temperature invariant, and that R is a constant, just going to be true. So then we can go ahead and integrate dt over t squared. Now, this is going to give me negative 1 over t. But since we're looking at a change, we're going to pull that negative sign out front, and we're going to have one, we're going to find the difference of the inverse temperatures. So 1 over the final temperature minus 1 over the initial temperature. And so this gets us our nice final. So then, because we have the natural log, we can get rid of that with an exponential. What we find is the ratio of pressures is going to be based on the negative exponential of the inverse difference in temperatures. So this is a little bit kind of an odd idea, but the important thing here is we have an exponential relationship. And again, we can now solve for our new vapor pressure as long as I have a reference pressure and a reference temperature. So if I know one point on my phase boundary, just like for the solid liquid, we can find the other one. And that generally this behavior is going to be exponential, and that the more positive that enthalpy of vaporization, the steeper the line. So this also means that sublimations will tend to have a much more steeper curve than vaporizations. And indeed, we can take a look at our general phase boundary and find all of these things are going to be relatively true. We have these exponential relationships in between the vapor and solid phase with a steeper line for sublimation. Then when I go to the enthalpy of vaporization from sublimation, the enthalpy is greater. So I see that slope drop down, but it still follows the exponential behavior and picks up again. Now, when we look at the solid liquid boundary, notice that this is relatively defined by a straight line. Note that if you put this on a log-based curve, you'll start to see this gets a little more curved because we have a larger pressure differences. And if you scale the axes, you can start to see that more exponential behavior. But under small changes, we can generally relate this as a simple change. So this is really going to be how we define our phase boundaries. Now, the important point is note that if you have a single point of reference, you can use these equations to build up the boundary in between solid liquid, solid vapor, and liquid vapor, as long as you have the enthalpies of transition and a reference point. And this is why we love the triple point, because using the triple point and those enthalpies, you can build up your entire phase diagram. So next time, we're going to finish up our modeling of phase transitions by using kind of an odd classification system to designate different types of phase transitions. Next up, the iron fest transitions. Until then, take care.